Have you ever wondered how machine learning models figure out the very best parameters to describe your data? It is like trying to find the perfect settings on a dial that makes everything align beautifully. This fundamental process often relies on a powerful statistical technique. Maximum likelihood estimation, or MLE, uses joint probability because its goal is to find the parameter values that make the asterisk entire set of observed data most probable. In essence, it asks, given this model and these parameters, how likely is it that we would have seen exactly the data we did? The parameters that maximize this likelihood are considered the best estimates. The core reason joint probability is essential lies in the nature of data observation. Typically, each data point in a dataset is assumed to be independently and identically distributed, meaning each observation does not influence the others and comes from the same underlying distribution. When events are independent, the probability of all asterisk of them happening together is simply the product of their individual probabilities. This product, encompassing every single data point, is precisely what we refer to as the joint probability of the entire dataset. So, how do we use this joint probability? We define a likelihood function, which is exactly this joint probability, but we treat the parameters as variables. Our task then becomes finding the values of these parameters that maximize this function. To make this maximization computationally feasible and numerically stable, we often take the natural logarithm of the likelihood function. This converts those tricky products into simpler sums. After that, we typically use calculus, taking the derivative with respect to each parameter and setting it to 0, to pinpoint the exact parameter values that yield the maximum likelihood. This approach provides a statistically coherent framework for parameter estimation. It embodies the likelihood principle, which states that all relevant information about the parameters in a statistical model is contained within this likelihood function. MLE is incredibly versatile and forms the bedrock for parameter estimation in countless models, from linear and logistic regression to advanced neural networks and deep learning architectures, providing robust estimates for complex systems. Therefore, maximum likelihood estimation leverages joint probability to offer a consistent and powerful method for inferring the most plausible model parameters from your observed data. It elegantly connects the probability of individual observations to the overall explanation of the entire dataset, guiding you to the optimal model that best reflects reality based on what you have seen.